All right, welcome back to differential equations here. So today we're going to begin our discussion about something called the Laplace Transform. Okay, so this is like the magic key to unlock how to solve a lot of differential equations without having to know a lot of different techniques. It is a little bit on the longer side, kind of like how quadratic formula is longer than just factoring in many cases, but it will allow you to do a lot more problems. Like maybe factoring doesn't quite work, or if you don't see it, instead of spending 20 minutes on guess and check, you can do this, and it'll take you 20 minutes to grind through it, but you're not going to get as frustrated with it. Okay, so the first thing we're just going to talk about is like what the heck is it, and how do you do one, and we'll get to how we're solving with it a little bit later. Okay, so the idea here is we're just going to start with the definition. Okay, so the notation, the definition, what we're going to do is we're going to say the Laplace transform, which is, I'm trying to make a curly bracket here, and I'm not doing a good job, but just use an L. Okay, have an f of t. Okay, and what this equals, this is f, and now we're going to eliminate the t variable, and we're going to have a parameter s. Okay, so we're going to get, it's going to change it from the time domain to the space domain here. Okay, and how we're going to do that is we're going to say that this is equal to the integral, the improper integral, right, from 0 to infinity, of e to the negative s, that's a script s, t, times f of t dt. Okay, and that's how that is our definition of a Laplace transform. So capital F of s looks like that. Okay, so we take our function, right, with a t in it. You could have an x, it's okay. And then we're going to multiply it by e to the negative s, whatever independent variable you have here. Okay, and then evaluate this interval. Okay, and that's what that's all there is to it. Okay. A lot of people get kind of hung up on the s. It's just a parameter for now. It's a new variable that we're introducing, so it's okay. It doesn't have a lot to do with anything going on with this. Okay, so just in the integral, we're not integrating with respect to s. It's not dependent on t. I mean, a little bit, but not something that's going to interfere with an integral. Okay. One thing we do have to make sure that we know is f of t must be of something called exponential order. Okay, because this works only if it exists, right? The Laplace transform only works if this integral actually exists. Okay, so if your f of t happens to look something like secant t, well, the limit as secant t goes off to infinity, right? As t goes off to infinity, secant is not a very nice function for that, right? Every time you get to a pi over 2, 3 pi over 2, 5 pi over 2, this thing shoots off to infinity, right? So f of t equals tangent of t. This is going to have a lot of asymptotes in it that shoots off to infinity. The limit, right, as t goes to infinity of this function just does not exist. Okay, the limit just does not exist. Okay, so regardless of what I multiply it by, right, this is not going to exist as an integral. Okay. Similarly, right, if we pick an f of t, that an e to the minus st is not going to dominate when you take the limit as t goes off to infinity. If we do something like e to the negative st of e to the t squared, right? I can't pick an s, right, where this term is going to go to 0 faster than this term is going to go off to infinity. So this is also not of exponential order. Okay, so when I say like, well, it's a very powerful way of solving differential equations, it is. Just realize that most of the functions that we deal with are of exponential order. The polynomials are all of exponential orders. Exponentials are of exponential order. Trig functions, sine and cosine, are of exponential order. Some aren't, right? These trig functions aren't. But most of the functions that you're going to deal with in like a real world type of a setting are going to be of exponential order. So that's why this remains to be a very powerful technique. Okay, so I want to warn you that not everything has a Laplace transform, because that's a favorite trick of math teachers to put on like final exams. So does this thing have a Laplace transform? Say, no, this doesn't have one because it's not of exponential order. Okay, but your engineering teachers wouldn't really like, oh yeah, I guess there could be something. They won't even, that will never come up. Okay, the thought of it wouldn't work would never occur to an electronics engineering teacher. Okay, maybe. I mean, I don't want to give them the proper credit, but most of your problems are not going to be dealing with stuff like this. When they do, there's other techniques. Okay, but for now, what we're going to do is make sure that we can actually make sure we can evaluate this interval. Okay, so why don't we look at some examples? Okay, and we can see what these look like. Okay, so if I want to take the Laplace transform of a constant, okay, what this is equal to the integral from 0 to infinity, right, of e to the negative st times a constant. Well, this is not so dt, right? This is not so bad, right? Because the constants, they move through the integral sign, so it's just really 1. Okay, so it's integral of e to the infinity, or sorry, 0 to infinity, e to the negative st dt. Right, what we're going to do, we can say let u is equal to negative s, du equals negative st, so this is negative s dt. So if I'm going to put, right, a 0 to a b, we have a c times the limit, as b goes to infinity, right? You're not going to have to do this every time, okay? When you did this in Calc 2, we dealt with improper integrals in Calc 2. We were really formal about it, and that's the class we will learn that in. This one, we're gonna be real lazy about replacing the infinity with a b here. Okay, but this is going to be e to the negative st. I'm going to need a negative s dt here, right, in order to get my du. But in order to multiply by negative s, what we have to do, right, is multiply by there. So I'll cancel. So here we have 0 to b, and t is 0, u is 0. When t goes to infinity, u goes to infinity. So we're going to have e to the u du. Right, we have a c over s negative, and we're going to have negative c over s, and limit e goes to infinity, right, of e to the negative st. Right? So just integrating that real quick. So we have negative c over s here. Okay, and now we have to deal with this. So as limit, right, as b goes to infinity, we have e to the negative sb minus e to the negative s times 0. Okay. Well, as b goes off to infinity, right, what is this limit? Right, this limit is 0. Minus t goes to 0, this is just e to the 0, which is 1. Negative c over s here times by negative 1 is equal to c over s. Okay, so the Laplace transform of a constant, right, is c over this new parameter s. All right, so that's for a constant. By the way, you're going to get a like the first time you do this, you have to do these by hand. But as soon as we're out of this section, you're going to be provided a table. You know, I'm going to put it on the last question of your quiz. You're going to get the table to do this. You're not just encouraged, like you have to use the table, okay, for some of them. So that's, you're going to be afforded a table to work your differential equations out with. All right, so let's see here. How about what if we try to take the Laplace transform of e to the at? Right, so exponential function. Well, that is equal to 0 to infinity e to the negative st e to the at dt. So let's make this a little bit better, right? This is the times here, right? So what happens for exponents? This is negative s plus a t dt, right? So just go ahead and integrate this. So that's going to be 1 over negative s plus a, right? And then we have e to the negative s plus a t. We have to evaluate from 0 to infinity, okay? So we're going to have 1 over negative s plus a. As t goes off to infinity, right, this limit exists. It's going to be 0 minus, if I put a 0 in for t, this is going to be e to the 0, which is going to be 1. I hope you're seeing a pattern here, right? And this is going to be negative 1 over negative s plus a. So that's going to be 1 over, that's going to be 1 over s minus a. Put the negative instead here. Now, again, this limit exists provided, right? Provided s is greater than a. Here, see, I should have noted this. So if s is a negative number, right, this doesn't exist, right? Because if we get negative times a negative, right, this negative times a negative is going to be positive. As s goes to infinity, or sorry, as t goes to infinity, this is going to blow up. Limit's not going to exist anymore. So we should put a little s is greater than 0 here. Right? That's the only kind of restriction you have to deal with. And this one, s has to be greater than a. All right. So, and that this is not a huge problem. Okay. So we're just going to note that s has to be greater than a when we do this. Okay. Take the most restrictive case. If you've got you're taking the Laplace transform, and in one Laplace transform, you've got s has to be greater than 0, and the other one has to be greater than 3. S is greater than 3. Okay, so take the most restrictive case. So let's see here. How about a polynomial? Okay, so why don't we try taking the Laplace transform of something like t? Okay, so this is going to be integral from 0 to infinity. Then we're going to have t e to the negative st dt. Oh, we have to do integration by parts. So how can you argue with that? So let u is equal to t, du equals dt, dv is equal to e to the negative st, v is equal to 1 over negative s, e to the negative st. Right? So we'll do our little box here. Right? So this is going to be t e to the negative st. There's a 1 over negative s here, right? It's this one. So that's t times this part minus integral. And then we have negative 1 over s e to the negative st dt. Okay. So what do we have here? We have negative 1, we have negative t over s e to the negative st plus, right, negative times negative, plus 1 over s e to the negative st dt. Okay, and we still have to integrate this. This is not going to be so bad. So this is going to be negative t over s e to the negative st. And again, we're going to have a minus, right? Because there's going to integrate. That's 1 over s squared e to the negative st, evaluated from 0 to infinity. Okay? So again, if we have to do a u substitution here, right, u would equal to negative st then du would be negative s dt, and we could go ahead and put the s in here, put the s down here to make it come out. We have the negative sign, so we're all good. All right. So if we need a couple of extra steps here, that's okay. But I think we're okay to go this fast at this point. Okay. So let's take a look. Let's take the limit, right, as t goes to infinity of negative t over s e to the negative st minus 1 over s squared e to the negative st. Okay. So that's one side of it. Minus, we have 0 over s e to the negative s times 0 minus 1 over s squared e to the negative s times 0. Okay, so as t goes off to infinity here, right, we have this limit, right? We have effectively t over e to the st here, don't we? Right, there's 1 over s. So when we're looking at this limit, right, we could use L'Hopital's, right? And I don't know the last time you've done a t e to the negative x e to the negative x kind of a limit. Okay, but I'm going to say by inspection. The exponential goes to 0 much faster than this t goes off to infinity. Okay, so this is the controlling term. And again, if you wanted to do L'Hopital's, that's fine, right? Take the derivative of the top end because we get infinity over infinity. That's 1 over e to the st times s. Now we take the limit. Right, this is going to go to infinity, so 1 over infinity, this goes to 0. Okay. Minus, and again, as t goes off to infinity, the rest of this stuff is constant, 0. Okay, minus. Now, 0 times 1, 0. And minus 1 over s squared, right, because that's 1. So we have here, right, we have just minus 0 minus 1 over s squared, which is 1 over s squared. Okay, so the Laplace transform of t is 1 over s squared. I'm going to pause for a second here. There we go. So that is the Laplace transform of t. Okay. Let's see here. Do we want to do t squared? Sure we do. Okay, so the Laplace transform of t squared. Okay, this is going to be integral from 0 to infinity, right? T squared e to the negative st. Oh, negative st dt. Okay, and oh, look at this. We get to do integration by parts again. So let u equal t squared, du is equal to 2t, dv is equal to e to the negative st, v is equal to 1 over s negative e to the negative st. So our uv, right, that's t squared e to the negative st. There's a negative 1 over s here, right? Minus integral negative 1 over s e to the negative st, right, times 2t. So let's clean this up. Okay, so here we have negative t squared over s e to the negative st plus negative times negative. We have 1 over s. Actually, we have 2 over s here, don't we? We have 2 over s t e to the negative st. Okay. Hey, you wouldn't happen to remember, like from the previous problem or anything like that, what the integral from 0 to infinity of was of t e to the negative st, right? We could go back up here, right? And take a look at this. What was this integral? Well, this integral was 1 over s squared, wasn't it? So let's go ahead and we're just going to take this out here and we're just going to put this aside and say this is 2 over s times 1 over s squared. Okay, that was that whole limit. Everything was evaluated. Now we just have to evaluate negative t squared over s, e to the negative st, from 0 to infinity. Okay, this same argument's going to go, right? As the limit, as t goes off to infinity here, we have 1 over s negative. We have a t squared over an e to the st. Right? That's what this means. And by the same idea, right? If you don't believe, you say, well, I'm not really sure, right? We could do L'Hopital's because we have an infinity over an infinity situation here. So this is negative 1 over s. We have a 2t e to the st times s. Well, that didn't resolve anything, so let's use L'Hopital's again. So we have 2 over, right? This is s squared e to the st. There's a 1 over s down front here. So we could look at this limit, right, as t goes off to infinity and say, oh, 2 over infinity, 0. Okay. So this piece here, that's all we're talking about, just this piece here. This is just going to be 0. If I put 0 in for t, 0 in for t, we get 1. 0 times 1, 0. Right? So this was going to be plus 2 over s. And using our previous amount here from the previous problem, right, we end up with 2 over s cubed. Okay, so the Laplace transform of t squared is equal to 2 over s to the 3. Okay. Let's see. Do we want to do t cubed? Maybe. All right. So we're going to do this really short here. So t cubed. Okay. What if I want to do something more interesting? What if I want to do like an at cubed, like a constant times a t cubed? So I want to do the Laplace transform, right, of a c times t cubed. Well, what's this going to look like, right? This is going to be integral from 0 to infinity of c times t cubed e to the negative st. This is going to be c times integral 0 to infinity t cubed e to the negative st dt's. Okay, so without going through this too much, right, we could say that the Laplace transform of a constant times a function is equal to that constant times the Laplace transform of that function. Okay, so if you're ever confronted with the coefficient in front of it, that's fine. The coefficient just moves through the Laplace transform, just like the constant moves to the integral. Okay. Furthermore, we'll get back to this. If I take the Laplace transform of, say, an a times f of t plus a b times g of t, what's that going to look like? Well, that's the Laplace transform, right? Well, that equals, don't do the Laplace transform. That equals a, let's keep all the steps in the right order here. That's a e to the negative st f of t plus b e to the negative st g of t, right? That's, again, I got to keep things in the right order. Let's go back and not put that in just yet. All right, there we go. So this is e to the negative st. I have a f of t plus b g of t. Which is equal to 0 to infinity, which is equal to 0 to infinity a e to the negative st times f of t plus b e to the negative st times g of t, right? Because that's how distributing works. And then integrals, right? We can take the integral and integrate each one of these things. So that's going to be integral of e to the, or 0 to infinity of a e to the negative st f of t plus integral, so dt here, 0 to infinity, there's a b, e to the negative st times g of t dt. And isn't this piece here, right? Isn't that just the Laplace transform of t plus b? And isn't this the Laplace transform of g of t? Yeah, it is. That's how that works. So it's really nice that the Laplace transform of a f of t plus b g of t, right, is equal to this piece right here. So again, if you're in linear algebra at this point, you're studying linear transformations, guess what the Laplace transform is? Okay, so that's kind of a cool thing that the Laplace transform is a linear transformation. This is also going to be helpful because when we're going to solve differential equations, we're going to take the Laplace transform on both sides, and if you have a bunch of stuff on one side, we're going to be able to apply Laplace transform to each term on each side. Okay, unlike, right, if I had like if I have an e to the x plus x squared plus sine x is equal to some function, right? And you say, oh, there's an e to the x in there. I can take a logarithm. Okay. You may have done this yourself, right? When you first learned about logarithms. Hopefully you will never do this again. Okay. But you can't, right? We can't do this, right? We can't say this is ln e to the x plus ln x squared plus ln sine x, right? That's you're going to be very unhappy. We're both going to be very unhappy. You're going to be more unhappy, but I'm going to be unhappy too. So you can't do that. But with Laplace transform, you can. Okay. So just be careful. You can't do this with everything. Okay. It has to be special. Has to be linear transformations. Then we can do it. Okay. But don't distribute logarithms through your sines too. Don't do that. Okay. Okay. Back to the problem at hand. Right. We had to take the Laplace transform t cubed. That was equal to integral e to infinity. Sorry for the tangent. E to the negative st. Okay. dt. Right. So what we're going to have is, we got to do integration by parts 3 times. Not really, because we already did squared. But we're going to let u is equal to t cubed, du is equal to 3t squared, dv is equal to e to the negative st, v is equal to 1 over s negative e to the negative st. So we're going to have negative t cubed over s, right? That's the diagonal part of the box, minus, and then we have the integral, and then we have the horizontal part of the box. So this is going to be 3t squared, 3 over s t squared, negative, right? There's a negative at 1 over s, negative 1 over s, t cubed, e to the negative st. Okay, let's clean this up just a little bit. Okay, so we have negative t cubed over s, terrible s's. By the way, it doesn't matter to me if you use an s or an s. My s's look like 5s, that's why I go to a script s, but there it is. Okay, and this is plus integral 0 to infinity of 3 over s, right? Negative times negative is positive. t squared e to the negative st. And again, we're evaluating between 0 to infinity here. Same argument that we had in the previous two problems, right? That this limit here, this is 0 minus 0. Okay. And then we have 3 over s. What did we find the Laplace transform? What did we find the integral of s of t squared e to the negative st was, right? We have an answer for this. That's the previous result we had, right? This is going to be, right, 2 over s cubed. This is 2 over s cubed. So this is 3 times 2. I'm going to put in a times 1 over s to the 4th. This was equal to the Laplace transform of t cubed. Can we make a rule for this? Right? Can we make a rule saying the Laplace transform of t to the n is equal to n factorial over s to the n plus 1? And so that, yeah, we could do that. And that'll show up on your table as well. Okay. So that is, that is a Laplace transform of your basic functions. Okay, so we know how to do constants, we know how to do exponentials, and we know how to do polynomials. Okay, in your homework, you're probably going to have to take the Laplace transform of things like sine, okay, or the Laplace transform of cosine. Okay, so that's going to look like e to the negative st sine t integral. And if you remember your integration by parts problems that introduce these, right, you're going to have to do integration by parts twice. You're going to get this huge thing. There's going to be, right, you're going to flip it. It's going to go to a cosine. You say, oh, I've got to do it again. You're going to come back to a sine. And it looks like it's going to go on forever. But the trick is that you swing one of these back over on the other side, and you do it that way. So it's one of those double, you have to do integration by parts twice, but one of them eventually swings to the other side so you can combine terms. Same thing with cosine. I might do one of those a little bit later, but mostly those, when I did this face-to-face, this would be like your exercise for the day kind of a thing, is to do this one. So I'm going to go ahead and stop us at this point, because we know we've done Laplace transforms, but that's just the beginning of it. Okay, there's a lot more to it, but be comfortable with this idea, and then we can go on from there. Okay, thank you, and we'll talk later.